Hello, everyone. My name is Josh Clabbers. My group mates are Ethan Campbell, Logan Donnelly, David Mulligan, and Ethan Sanders. And our presentation is entitled The Mothership. So the concept for our idea is that large-scale UAV integration into fire safety would allow for really, really fast reaction times to fires of all types, but particularly forest fires is what we're focusing on. But the big leading limiting factor is the ability for the drones to actually carry enough water to effectively fight those fires. Oftentimes you see that in the integrations we've seen so far, they are able to carry water and spray water where they designate. However, there's just simply not enough water to actually be effective. And that's the main problem we're trying to solve here. So enabling UAVs to use their speed and precision to target the weaknesses in the fire using their water payload, but then allowing them to refill by returning to some sort of station. They go get the water, then they come back to the fire and continuously do that process until the fire is essentially extinguished, if that makes sense. So that's what we're trying to do here. So our concept is essentially a mothership blimp that houses a large amount of water. And then it also has basically an army or a swarm of UAVs. And putting these all together would present an effective method in fighting fires. The blimp would essentially fly over fires and deploy the drones to dump their payload, return and refill, and continue using their payload until the fire is put out. The blimp would be the main communicator. Basically, swarms or large armies like this need sort of a central communication that designates, where the drones would, where each individual drone would put their payload, making sure that they don't run into each other, things like that. We could either have, sensors on each individual drone for collision avoidance, or we could still have the main blimpy, that main communicator that's constantly scanning where each drone is. But the fast takeoff time of these blimps would allow for quicker and more effective firefighting in remote areas. Oftentimes, forest fires get out of hand because there's a slow response time. It's hard to get equipment and people out there, and the distance can be far away. But if we have sort of a blimp that's on standby, ready to deploy, it could easily just take off and get to the fire and start trying to contain it as fast as possible before the rest of the response arrives at the fire to help contain it. So here's a little video. This is actually just a fake concept video for an Amazon blimp that actually just carries the packages instead of water. And so the drones come up, get the package, and come back down. But it's kind of a similar concept. So you can see the way the drones all kind of exit the blimp, go do their thing. And then eventually they would come back. And that's all for me. Thanks.
Hey guys, it's Ethan Campbell. I'm going to continue on our presentation here for our ship UAV project. I want to begin with our first problem, that is cost-related complications. Before I begin, I wanted to briefly mention, I don't want to get too in-depth with some of these complications because they would bleed it over into complexity, though I will go as in-depth as possible with these cost-related complications without entering into the complexity section of the presentation. So I wanted to begin with the list of cost-related complications. First off, cost of fuel. Second, cost of equipment. And finally, possible cost of replacing UAVs. So The cost of fuel, of course, is obvious. You're going to need a lot of fuel to get such a large project off the ground, as well as a good number of I guess battery fuel sources to recharge drones. So you have gas fuel or jet fuel, some type of fuel there that's going to be able to lift a large project off the ground. That is going to be a considerable cost, and then of course the batteries to charge the drone. Next up is cost of equipment. So this is kind of, I'm going to lump a bunch of things into this. First, want to begin with the actual project itself. Of course, a very considerable cost. And then, of course, the cost of UAVs to purchase. You could be talking about thousands of dollars there. Um, excuse me. And then just any maintenance equipment that may be needed should be lumped into that cost of equipment as well. Finally, the possible cost of replacing UAVs. So I've kind of talked about considerable cost-related complications. I think this one plays into that very well. Like I had mentioned, with drones, you could be talking about thousands of dollars. So any drones that may be damaged or even destroyed in a wildfire would need to be replaced. And of course, that cost would add up. So of course, you want to add that to the list of cost-related complications. And then for solutions, I have two listed here, levies and federal funding. First, I wanted to begin with maybe the least plausible, and that would be levies. So levies are funded, of course, at the local level through property taxes. These levies are really a big funding source for maybe medium sized apartments, but with this project, I could see where levies maybe don't make the cut. There's some ways you may be able to make it work, but again, levies may be too small a funding and may not fund the entire project. And then finally, federal funding. I think this is the most plausible out of the two, with wildfires affecting a lot of national parks or even lands with some federal interest to them. The government, of course, would want to protect them, and therefore they would be able to fund such a project like this, or bring this project to light for the fire departments who would be using it. So those were that was the first problem, cost-related complications and their solutions. I'm going to go ahead and end the recording here and pass it over to the next person to continue on the presentation.
Hey guys, I'm Logan Donnelly, and as Ethan mentioned, I'll be discussing some of the issues involving the complexity of our application. So the first issue is the autonomous implementation. Because there's so many individual worker drones, we decided it would be best to implement the system autonomously because it would be too hard to control each of the individual worker drones manually with a human pilot. And with any sort of autonomous system, there comes a lot of complexity. How we envisioned our system would work is the individual worker drones would sort of relay some information back to the mothership, like their position and what the current task they're performing is. And then the mothership would use this information to sort of coordinate the drones in the most effective way and like divide up the individual tasks between them. And to do all this, there's a lot of complexity involving the wireless communication and like the software you'd have to use to sort of design this behavior. And that's why it would be complex to implement. The second issue involving complexity is refilling the worker drones with water. So how we envisioned that working is the worker drones would come to the mothership and they would each be equipped with some sort of physical apparatus like a tube and a pump, and that would allow them to sort of refill with water from the mothership. And this is just a sort of complex task to implement, especially autonomously. You'd have to have the drones hover over the water, and the system on board would have to allow the pump to pump the water into the worker drones. and all that is difficult to implement. And third is the sort of interdepartmental coordination between different fire departments, because this system would likely be used by several different fire departments. Depending on the location of the wildfire, there would need to be some sort of protocol in place for how these different fire departments would communicate with how the system's being deployed, who gets to use it, and how it's going to be deployed, what locations is the best place, and all that would be sort of a complex task to have, especially like with regulations in between the different fire departments. So these are just three of the main complex issues with our implementation. And now I'll pass it off to David.
All right, now let's move on to the last problem, which is reliability. So one complication was trying to create a reliable system for putting out wildfires using a mothership and a drone swarm is the lifting capability. In the next section, Ethan is going to talk a little bit about lifting capabilities for the drone swarm themselves. So I'm going to talk mostly about the airship. So water is a very heavy substance, and we need a lot of it to put out wildfires. We need about 40 gallons per acre based on historical data, and that would be equivalent to 334 pounds of water per acre, which is a lot. So the solution for that is that we do know current airship technology, at least on a very high level, can lift up to 500,000 pounds. So that means that based on the same historical data I just referenced, we'd be able to put out fires up to 1,400 acres. Anything larger than that would require either a refill or the use of multiple airships, and that's going to be determined on a case-by-case basis. If there is fresh water available nearby, then we will certainly use that to refill. Otherwise, we would have to use multiple airships, assuming we have multiple available. But one thing to consider that might make this a little more feasible is that we're trying to improve the efficiency of putting out wildfires. So even if we could improve that efficiency by, say, 20%, then we would only need 32 gallons of water per acre to put out the fire instead of 40, meaning we can put out fires better, more efficiently using less water. The next complication is that we have power supply limitations. So batteries are very heavy, and they also don't have a fantastic power output. And we don't want to be putting things that are too heavy onto the drones because that would take away from the amount of water that they can carry with them. Also, because we're lifting these heavy tanks and hoses full of water, it's going to drain the power faster than if we were just doing regular aerial maneuvers in the drone. So our solution to that is putting charging stations on the mothership. You can see the picture on the right. We have these lightweight charging pads that would make for quick and easy linkage to the drones. And we're thinking of just lining the bottom of the mothership with these charging stations. Since we're going to be sending drones back to charge, that would definitely require a slight surplus of drones because we want to make sure that at all times we have enough drones actively putting out fires that we are able to maintain and put that out. So for example, say we need 100 drones for this particular fire, we would actually deploy 120 of them, acting under the assumption that at any given point, 20 of them may be back in the mothership charging. And hopefully this would allow us to put out the fire in a fast and easy manner.
The overall design of the mothership would require successful integration of multiple existing technologies. On the UAS side of things, this mainly includes drone swarms, heavy lift UAS, and looking at the current implementations of UAS technology in firefighting specializations. First, drone swarms. Drone swarm technology is a very rapidly developing topic today, and it is basically the ability for drones to coordinate with each other in large numbers and in close proximity to complete a common goal. There are many applications for this technology, but one of the key areas of research is for military applications to create swarms of loitering munitions. This is effectively a UAV swarm that can loiter over a large area and collectively identify and engage targets in this area. With regards to wildfire fighting, it's kind of easy to see how such a technology is actually quite similar. A wildfire fighting drone swarm would be able to identify, whether that be autonomously or by a human controller, areas of opportunity for most effectively fighting a wildfire and continuously attack that area with water. It also allows an easy way to greatly multiply the effectiveness of a drone by, well, simply adding more drones. On the right here on the slides is a visualization of how a similar drone swarm might look, but this one is using a land-based hub instead of an aerial hub as we are proposing. Next is heavy lift UAS technology. Simply put, water is heavy, almost 8.5 pounds per gallon. A Type 2 tactical water tender that you might see providing water to these wildfires can carry 1,000 gallons of water. An example is shown on the top left. By comparison, a Bombardier 415 water bomber, shown in the top right, can carry 1,620 gallons. Given no reference point on the aircraft, it can be hard to tell, but the 415 is 66 feet long and has a 95-foot wingspan, which is significantly larger than the relatively small truck and can only carry a little over 1.5 times the water. Weight is crucial when taking into account a vehicle that functions by counteracting its weight, and a UAV is no different. On the bottom is a heavy lift UAS called the Volocopter Volodrone, which is supposed to be used for agricultural spraying, but has a potential 440-pound payload. This is only around 55 gallons of water. Very quickly, it becomes apparent the usefulness of drone swarm technology. However, heavy lift drone technology can not only decrease the amount of drones in the swarm, but also increase the firefighting capability of a single drone. The point being, throwing a bottle of water at a fire isn't going to do much, but by increasing water capacity per drone, you can increase the maximum intensity of fire that these drones can attack. Finally, some firefighting specific technologies and applications for drones have already been created and tested, and I would like to bring a few of those up. The Singular Aircraft Flyox, which is up there on the top right, or the Drone America Scooper drone, right below it, are both drones that have been considered for use in an autonomous water bomber system. However, as you can see, both of these are fixed-wing aircraft, and not quite what we need. On the other hand, there have been multiple instances of fire departments using quadcopter drones to hoist fire hoses up to fires in high-rise buildings, and have showed great usefulness in helping to control and extinguish these fires. For the purpose of our drones, they would essentially be a combination of these two. They would essentially be a multi-rotor water bomber.